First question then. First question was done really well by most people. We just had to state the angle of dip of the rocks at this grid reference. We can see if we go to 76.0, so 76, 167 is here, and if we scroll in a bit more we can see there's the answer. So the answer was 75 degrees, and that can just go in there and that would be your answer. What was found much more difficult was question part 2. Now if you remember from the map, the symbol was like this with 75 written next to it, and all they're asking you to describe how you would work out it was 75 degrees if you were there in the field. And the piece of equipment you'd need to use, you'd need to have a clinometer. Now a clinometer measures the angle of dip, and to measure the angle of dip you would find the steepest angle, which is true dip. Now you got a mark for saying that, and you also got a mark for saying that this would be 90 degrees to the strike. Now the strike we know is northeast to southwest, looking at that orientation, and the third mark would be to say that the dip was pointing towards the southeast. Very simple question, but made very complicated by a lot of you. Next part was looking at the Southern Upland Fault. It says it's been active for a long time and it's been reactivated more recently, and they just wanted you to find the characteristics of the fault using the map alone. So you had to find the strike direction, the down throw side, and then that would lead to the fault type. They already tell you that it dips northwest at 85 degrees, so we know the fault dips towards the northwest at 85 degrees. And if we were to draw a little section of that, northwest would be this side and southeast that side. So we're doing a transect from this point across the fault line like this. We know the fault dips steeply 85 degrees towards the northwest. Now we need to know which the down throw side is, and if you look very carefully over here there's a little cross mark. The cross mark is on the northwest side, so we now know this side has gone down and that side must have gone up. Now straight away most of you would realise that if the fault dips towards the down throw it must be a normal fault, and if you don't believe me, if you draw a bed of rock in here on the down throw side, it must have gone up on the up throw side, and you should see that the whole thing has been lengthened. There's a gap down the middle, and the hanging wall has gone down as well, which is also characteristic of a normal fault. So what they wanted you to tell you was the down throw side is to the northwest and it's a normal fault, and it strikes northeast to southwest. And part C was looking at this granodiorite igneous batholith or pluton just here, and all they want you to do is work out the maximum and minimum width of the metamorphorial south of the grid line 18. So there's grid line 18, and south of that line, so if we put a line on there to remind ourselves, so south of this line you had to work out the thickness or the width of the outcrop. Now the maximum is obviously the biggest, which is probably either here, or if I had a ruler there would probably be the biggest, and if you measured that, that came out as about anything between 750 metres and 1000 metres. Now the minimum is over here, and that came out to about 250 to 300 metres. Obviously you just measure it and use the scale at the bottom. Now there's a scale down here, and you just measure it and see how far it came across this scale. Simple as that for those marks. Now what most of you found difficult other than that was they ask you why would it be narrower here and wider there. It's the same intrusion, but it's obviously narrower here and wider there, and they're asking you how the dip of the igneous pluton might affect it. So let's draw the igneous pluton here, and there's the ground. That's a bit thick, so I'll do that again. Okay, we just get rid of this this thing here and start again. Right, so we have our surface. If we draw one side of the batholith very steeply and the other side at a shallower angle, and then we were to draw in the metamorphic aureole, trying to do the same thickness either side, and if you notice on the surface it's that thick or that wide, and it's wider on that side, so the shallower the angle of dip of the igneous body, the wider the outcrop width. This is obviously steeper, and so it's a narrower outcrop width. The last part of the question asks you to give one other possible explanation for the thickness of this outcrop of metamorphic aureole, and there could be a number of things. This area here could be a rock that is more susceptible to change. It could be more this one actually, this would be less susceptible to change because it's narrower. The wider one would be more susceptible to change. Maybe the rocks are more thermally conductive, so the heat could transfer further. Maybe there were fluids in this area. Obviously water conducts heat much quicker than air, so you would transfer the heat further. It's a whole variety of things that you could put down to get the answers for that question.